Hi everyone, welcome back to another video. Hope you're all well. So we're just swinging through the Practical Electronics for Inventors book. I'm going through AC, hopefully trying to get up to scratch with my lectures, which currently I don't understand, but I feel like I'm getting somewhere. So in the last video we covered root mean squared voltage and current, so RMS voltage and RMS current. We went through these two equations here. So let's build upon that now. So we went through this example. We covered some of the Ohm's law powers. I'm doing it again. I forgot to press record on my iPad. Let me press record because on the last video I didn't record either. Okay, and now I'm recording on the iPad. All good. Okay, so we covered AC Ohm's law and AC Power's law. AC power law. AC power law is it? Because it says it here. Let's find it. Into Ohm's power law to get what's called the So it's called the AC power law. So this is the AC power law here. So basically the AC power law is power dissipated is equal to the root mean squared current multiplied by the voltage root mean squared, or the root mean squared voltage, right? And then obviously you can manipulate V equals IR to get these two equations as well. Again, these equations apply only to circuits that are purely resistive, meaning there is virtually no capacitance or inductance. Okay. I remember writing that up here. Let's have a look. I wrote something similar, but I didn't know that's what it meant about it being okay. When AC source is connected to purely resistive load. Okay, so I didn't know that a resistive load means it only has resistance. It doesn't have capacitors or inductors. So let's write that down. So purely resistive load is equal to no capacitance or inductance. Okay. So these equations only apply to circuits that are purely resistive. Right, so let's just put like a warning sign here. These only apply to resistive circuits. Just put purely resistive circuits. Okay, all good. Doing power calculations on circuits with inductance and capacitance is a bit more complicated, as we'll see a bit later. I love that. I love the fact that they haven't introduced inductors and capacitors. They don't start explaining it. They just say, look, it's complicated. We'll explain later. That's great teaching. I love it. So figure 2.87 shows relationships between RMS, peak, peak to peak, and half wave. What's a half wave? Is that like that's on either above or below zero, not crossing zero? So figure 2.87 shows all of these, the relationships between these average values of voltage and current. Being able to convert from one type to another is important. One type of what? RMS to peak. Okay, yeah, got it. So being able to do these equations basically, where are we? Being able to do VRMS is equal to 0.707 times the voltage peak. So they're talking about being able to convert from peak voltage to RMS voltage. And I don't know how you'd get peak to peak or half wave. Okay. Especially when dealing with component, maximum voltage, and current ratings. Sometimes you'll be given the peak value, other times the RMS value. Understanding the difference also becomes crucial when making test measurements. See the note on pages 91 to 92 about making RMS test measurements. 91 to 92. That's the next page. Okay. Most of the time, when dealing with AC voltage, you can assume that voltage is expressed as an RMS value, unless otherwise stated. Yeah. Okay. When dealing with this is okay. Yeah, AC voltage. Got it. Okay. So they were saying something about up here. Figure 2.87 shows the relationships between RMS. The 2 point, was it 2.87? Is it this one, or are we talking about this here? The relationships between, so from peak to peak, you just multiply by 2. Why is that? So this is the peak here. And then, so if you had a whole wave from going down along this way and back up to here, the next one's going to be here. So what does it mean that you multiply by 2? So so what's this? This voltage or current? This is both the voltage peak or current peak. Either or, right? Okay, so let's say it's voltage. So 1 volt here, and so you're saying that you just times it by 2. How does that make sense? To get the peak. So that would mean that the okay, I don't understand that one. I should probably just jot these down even if I don't really understand them. Or at least maybe take a picture of it. From peak to peak, just peak, you divide by 2. Well, that makes sense. If the top one's true, then that's the bottom one as well. From peak to RMS, we already know. You multiply by 0.7071, and then RMS to peak, you multiply by 1.414. They didn't include the 2 last time, but okay. And then peak to peak, this is all a little bit confusing, but all right, what I'm gonna do is I'm just gonna take a picture of it instead of writing it down because I don't really actually understand it. So probably better in my interest to just skip on for now because I don't understand where we're getting peak to peak from. But what I can do is I can just put relationships to memorize. Put that in it. An orange color or something. Okay. Okay, so let's look at an example. I didn't really understand this bit here, but it'll be okay. All right. So how much current would flow through a 100 ohm resistor connected across the hot and neutral sockets of a 120 volt AC outlet? Okay, so we're just doing V equals IR, right? So let's put example 1, and then we're gonna say V is equal to IR, and we're also gonna take that Ohm's law one here, AC here, and so we're trying to find current, right? Is it current? Yeah, current through 100 ohm resistor connected across 120 across 120 VAC. Okay, so we just do V RMS, right, divided by R is equal to IRMS. Okay, so we're just doing 120 ohm, 120 volts divided by 100 is equal to 1.2 amps. Okay, so how much power would be dissipated? How much power would be dissipated? Okay, so let me just do my workings out in a different color so I can kind of, right, how much power So we just take the power, AC power law, is this one here. Paste this in here. Okay, so power is equal to the current times the voltage. So you just get P is equal to 1.2 times 120. So P is equal to, I better do that in my head, 144. 144 watts. Okay, any more? How much power would be dissipated? What would the results be using 1,000, 10,000, and 100,000? Okay, so let's just make this bit blue again. And then we can say, how about, what was it? 1K ohms, 10K ohms, and was it 100K ohms? Is that correct? 10K, 100K, yeah. Okay, so we just take this same equation here. I mean, it's just going to be like magnitudes of 10 lower, right? So we've already worked out that through a 100 ohm resistor, you get 120 over 100 gives you 1.2 amps. That's for 100 ohms. So 1,000 ohms is just going to be 120 divided by 1,000, which is going to be what, 0.12 amps. And then 10,000, it's just going to be 0.012 amps, and 100,000 is going to be 0.0012 amps. All right, let's see if I'm correct. Okay, so VRMS is equal to IRMS times R, which is 120. Okay, they've given us the answer. The answer is just here, but we're supposed to work it out. Okay, 120 volts divided by 100 ohms is 1.2 amps. 120 volts divided by 1.2, 100 ohms. Okay, power average 144. So I was right about those. So didn't give me the. Oh, did it? Okay. All right. So first, don't try this with an ordinary resistor. I've got a video up actually. If I remember to, I'll stick it here. Where I put 30 volts through a resistor. Take a look at that. That's quite funny. That's 30 volts. So I would love to see what happened if you put 120 volts through a standard resistor. You need the power resistor or a special heating element with a power rating of greater than 144 watts. Also, simply don't attempt attaching a resistor with the outlets. Oh man, Electro Boom, you've got to watch it. The guy on YouTube is brilliant if you want to see people sticking stuff in outlets. So 1,000 ohm resistor plugged into the same outlet would dissipate. Oh, what was I asked? Oh, what would the results be? I worked out what the current would be. But we're supposed to be checking. Oh, okay. Wait. So, okay, yeah. So I would just basically work these out like this. If I was working out the power, wanted to work out the power, I'd have this, and then I'd do P is equal to. This is for the 1,001. I'd do 0.12 times 120, and then that would give me 14.4 watts. I've seen some YouTube videos of them calculating, like how much they need, what power rating, what resistor rating, etc. And so this is obviously how it's done. I was always wondering that. Here we'd get 0.012 times 120, and that would give us 1.44 watts of power dissipation. And here we'd have 0.0012 times 120 volts, and that would give us 0.144 watts. Interesting. 1,000 ohm resistor plugged into the same outlet would dissipate 14.4 watts. 10,000 resistor would dissipate 1.44, and 100,000 resistor would dissipate 0.14. Nice. Very happy with that. Okay, so let's move on to example 2. How many examples are there? This is good that they've got these examples at the end of the chapter. The 6 examples. So what we'll do is we'll do example up to example 2 in this video. So we'll do this next example, and then in the next video we'll do 3, 4, 5, and 6. Just because, like I always say, I want to try and keep these videos a bit shorter. Okay, so if you're not on the playlist, go in the description or in the comments. So if I remember, I'll stick it in, and yeah, watch the playlist, because then that way you can just get the whole flow. Okay, so example 2. What is the peak voltage on a capacitor? Okay, capacitor. What is the peak voltage on a capacitor if the RMS voltage of a sinusoidal wave, so a sine wave, signal across it is 10 volts? This is I don't know why they're chucking in capacitor here in this question, but basically it's a bit of a trick, right? Because the voltage, across the capacitor, it's got nothing to do with it. It's just whatever in it. So basically, what is the peak voltage? If the RMS voltage of a sine wave is 10 volts, that's it. It's just simple. It's not, the capacitor is irrelevant here in this question, right? So peak voltage, if RMS voltage is 10. Okay, so an easy way to think about this is that we're saying here that we've got a sine wave like this, right? And we're saying this value here, what is it? When we know that, the RMS value, I don't know how I would draw it, but the RMS value I assume would look something like this or something, right? Or something like this. But anyways, it works out to be like, the average kind of the root mean square value. So it's going to be lower. Sorry, the RMS value is obviously lower than the peak voltage. The peak is the max voltage. So we're saying that here is 10. So this is obviously going to be like 12, 13 or something. So we just remember that calculation where we're just taking voltage peak is equal to, I'm doing this from memory, so let's see if I get it right. Voltage peak is equal to voltage RMS times 1.414. Am I correct? Yeah. 1.414 times 10, and that obviously equals 14.14 volts. And that is the voltage peak. Nice. You got it there. I'm very happy with that. I feel good. If I don't know if you've been following me with this, but in the beginning I basically wanted to cry, and now I'm feeling very good. So cool. In the next video we'll do 3, 4, 5, and 6. Let's get on this, man. I'm excited. See you in the next video.